So this video is going to discuss how it is that we are going to take a look at some properties of what happens if I have not just one linear function, what happens if I have two linear functions that are interacting together and they're being linked together on the same coordinate plane. So one of the things I like to talk about here is that this is not a graph, and I know a lot of people may say, what do you mean it's not a graph? I've always been told it's a graph. With nothing on here, this is your coordinate plane. It's not a graph. A graph is the actual visual image of a function that you have in either its representation form or its equation form. So what we're going to talk about today is literally the idea of what if I have two linear functions that are interacting on the same coordinate plane? So what is it that I can do? What are some things that I can observe? So first things first, let's just run back through our equations of lines. So the first equation I have up here is y equals mx plus b. This is probably the most famous equation of a line because it gives you details actually about the line, where it gives you how the line is behaving, how it's growing. So that is your m, which is your rate of change. And it also tells you where your initial value of where all your data begins from, and that is represented by b. The standard equation of a line, literally, it's just the standard form. It is literally just saying to you, multiply a number by x, add a number being multiplied by y to it, and you've got some answer. Okay, so C is you're going to get some value, and this form tells you literally nothing. You can graph from this form. And the way you graph from this form is by using x and y intercepts. Number three, this is the point slope form. This formula is generally used if you say know a rate of change and know a point and don't know the starting point, that there is a interconnected relationship that allows you to get back into this y equals mx plus b. So moving forward. So essentially our goal is to be able to, by the end of this video, understand that if two lines are graphed on the same coordinate plane, what can I observe? What am I looking for? What is this interaction that I'm talking about? So first things first, I have two lines here. So these two lines are a system. And how do I know it's a system? Easy enough. There's not just one equation. It's more than one equation for this particular problem. So the way that I go ahead and go through this one is I take a look at it and I go, okay, well, let's get a visual of y equals negative 1/6 x minus 4 out there. Now, the nice thing is that this is already in y equals mx plus b form. So what I already currently know are two things. I know, one, I know what its rate of change is, and the rate of change is always your multiplier or your coefficient of x. So if I mark that very quickly right there, my rate of change is always going to be negative 1/6, which basically means, okay, if I'm graphing this, that I'm going to have a right triangle connected to my line. All right, and I'll show you what I mean by that. It's called a slope triangle. I'm going to have a right triangle connected to my line that is going to have a height of 1 and a base of 6. So if I'm going to go ahead and graph this by hand, okay, one, I need to know how it changes. I also need to also figure out where on earth does it start from. And the value that it starts at is negative 4. So what this ends up being is this is called my initial value. All right? So the way I like to think of this is that if I graph points, generally we go to the origin of 0, 0. Well, this tells me, well, guess what? You're not starting at the origin, all right? You're starting somewhere else. And that's what this value does. So what this tells me to do is it says, hey, you can slide up or down, but guess what? You can't begin to go left or right. However, I can start out as being lower than 0 or above 0. I could start out at 0, but for this particular problem, we are starting at negative 4. So here we go. Let's go ahead and graph this particular line. So one, my starting value slides from the origin down to negative 4. So what I'm going to do is I'm going to indicate, hey, I'm not starting at the origin anymore. I'm starting at negative 4. So we mark that point off. Boom, there it is, marked. And now what I'm going to do is I'm going to use my directions that I highlighted up here in blue. So what this is my rate of change. So the way that I do this by hand is I draw a right triangle. And the right triangle that I'm going to draw is going to have a base of 6, so a base of 6, and a height of 1. Now, the thing that we need to keep in mind is that I can draw two types of triangles here. So the base could be 6 going 1, 2, 3, 4, 5, 6, okay? Now the question is, all right, the height of my triangle. Should I start going up or should I go down? So the question then becomes that to find that answer is actually found in whether the fraction is negative or positive. If the fraction is negative, all right, I am going to go down to my next point, because what I need to have is that I make a quick little visual here, all right, that this line should be going down. If I were to go up, this line is also then going up, okay? And I don't want that. I want a line that is descending, not going up. So I would go down, so there's that, and I put my point, okay? So what I meant by my right triangle, that if I were to only connect these points right here, notice that I literally have a right triangle that is drawn on my coordinate plane here, okay? However, we're not interested in drawing a right triangle, we're interested in drawing a line. And to draw a line, you would just continue on forever and ever. So I would just continue along this path. Now, to make this a little bit more exact for me, okay, I'm going to duplicate this triangle, because what it means to be linear is it means you're going to have a repeated pattern. So I'm going to duplicate this triangle again. So go up 1 and over 6. 1, 2, 3, okay, 4, 5, 6. And then I just keep going, right? So I mark my point, and notice that my line just keeps traveling. And I can continue on with this line, okay? So whoop, there it is. Sorry, it went a little, didn't go over very near far enough. All right, so we have our 6, right? So then my line continues on its pattern. Okay, so I hope you can see that. I'm going to get rid of these triangles in a second, but the point is that for graphing, these triangles are extremely important because you need to think of these as repeated triangles, so therefore that it becomes my linear. The top number in our rate of change is always the height of the triangle. The bottom number is always the base of the triangle, okay? So getting rid of those triangles, all right, whoops, erase some of that. All right, and I have this line, right? So there's line number 1. Line number 2. Line number 2 has a rate of change of 2 over 3, but starts at -9. So now instead of going the origin, I go down to -9. There it is, okay? So now again, all right, this is the height of my triangle. That's the base of my triangle that I'm going to draw. So the height of my triangle is 2, the base is 3. So it doesn't matter however you draw this right triangle, you just need to make sure you draw the right triangle correctly. So I'm going to have a base of 3, so 1, 2, 3, and a height of 2. So my base is 3 and my height is 2. Okay? Whether I choose to start by drawing the height in first or the base in first does not matter, but notice that, okay, then I continue on, so I go to another height, so I'm going to connect these, right? So now I can continue this on, draw my triangle in, okay, base of 3, height of 2, and I continue this on, and I keep going on forever and ever, okay? So just for this, I'm going to get rid of these triangles, so just for graphing purposes, all right? So what we end up now having is that now I want to observe, what do these two lines do? How do they interact? And the easiest answer to this is they clearly intersect, all right? Well, mathematically speaking, if things intersect, as a mathematician, then I want to know the data behind where they intersect. And that's all I want to know. So other than that, what do these two lines do on this coordinate plane? And the answer to that is nothing. So if the only thing that they do is interact by crossing, then the only data that I can collect is the fact that these two values cross. Okay? So we're going to collect that data. Where on earth do they cross? Well, to figure out that coordinate value, okay, we don't go to one of these points. Again, when you actually plot points, you need to start from the origin. So the way you start from the origin is we're going to go over 6, and then I'm going to go down to -5. So this point labeled on the graph is 6, -5. Okay? Now, there are some interesting things that happen here. Okay? So this is x and this is y. So what we begin to notice here is that, okay, well, each of these lines happens to go through an identical x and an identical y. And remember when we discussed earlier in the year about, hey, how do I check if a point is on a line? I plug it into the equation, correct? So if I were to plug this point 6, -5, and check in the equation, does it work? The answer to that is obviously yes. So mathematically, we're going to, a little bit later, talk about, all right, well, if mathematically, if I plug this single point and where they intersect into both of these equations, okay, it means that I'm making a true statement for both equations now. So therefore, this point works for both equations. And therefore, all I can say about these two interactions is that that point is the only place, okay, where these two things are ever going to have an identical solution. Because note, straight lines are only going to ever intersect one time. Okay, so moving a little forward, we're going to change this example up, and we're going to take a look at this ax plus by equals c form. So just to move along from this into a different example, all right. So we're now going to take a look at this 4x plus 3y equals 3. And we're also going to look at the other equation where x minus 3y equals negative 18. Now, it depends on how much work you really want to do here. But what I would begin to note is that I'm probably not going to use, as I mentioned before, x and y intercepts here. And the reason for that is if I plug 0 in for y, so notice that the y coordinate is the one that dictates whether I go up and down. So if I want to have a point on the x-axis, I have to have a y coordinate that says you can't go up or down. And the only number that tells me up or down is the y coordinate, and the number that tells me I can't go up and down is 0. So to stay horizontal from the origin, okay, then I would have to have a y coordinate as 0. Now, the reason I bring up that one for this particular equation is that if I plug 0 in for y and I solve for x, I'm going to get a decimal, and we generally don't really like to graph decimals because we can't really graph them as accurate as we would like to. So the other option we have is to take this ax plus by equals c and convert it into its y equals mx plus b form. So the first thing that I'm going to do to actually begin to look at the interactions of these is actually going to go through and convert it. So the way that I would convert it is I would say 4x plus 3y equals 3. Now some people might use the idea of inverse operations. So if you want to use inverse operations, that's fine. But the way that I kind of think about this is that, hey, if it's positive here, it's negative over here. So minus 4x over there. Now I want it in y equals mx plus b, so usually the coefficient comes before the number. So while this may be my work, the next time that I write it down here as 3y, I'm probably not going to write that. I'm probably going to write it as 3y equals this negative 4x, and it's a positive 3, so plus 3. Now, I wanted to say y equals. So the two things that were in my way were, one was this 4x, and the other one is this 3. So if I were to pretend this were just a number, well, how would I solve for y? Well, you would divide by 3. So I'm going to do that here. So now we just need to remember that when you use division, division is unlike addition and subtraction. Division is higher up on the orders of operations. Therefore, it holds more powers when you're using it in an equation. So I don't just get to divide one thing and then go over here and go, oh, I have two things. Which thing should I divide? All right? It's more powerful. It has more responsibility. Therefore, we must divide everything. So I divide everything by 3. And what I get is y is now equivalent to negative 4/3 x. And now the reason I didn't write that as a decimal, because I know the rookie mistake that a lot of people make is they go, oh, let's just do negative 4 divided by 3. And then you get a decimal. Well, slope is a ratio. It's a comparison of two numbers. A decimal is one number, so I leave it in fraction form so that I can actually graph it, because the whole purpose of putting something into y equals mx plus b is to recognize what its growth is, so I can talk about a triangle's base and height, its rate of change, all right? Where a decimal, I need two values to draw a triangle for a height and a base. A decimal is only one, can't do it. So I leave it in that form. Now plus 3 divided by 3 is 1. So what I have for this line is that I've converted it into this form, and now I can go ahead and look at its image on the graph. So again, this plus 1 here tells me that I can, in particularly, I don't know if you can see it on the, so y equals negative 4/3 x plus 1. So what this tells me, okay, is that I can go over to this graph and use this starting value, so plus 1. So boom, there's my new starting value for this graph. and I'm going to draw a triangle, okay, that has a height of 4. So the top number is the height, the bottom number is the base. It's going to be a right triangle. Okay, so to draw a right triangle, I have great grid lines here for me. So the height is 4, the base is 3. Now, I just need to keep in mind, should my line be going up or should my line be going down? And this is the easiest thing in the world to determine, because if it's negative, it goes down, as we always associate negatives, and if it's positive, it goes up. So this line, when I draw this right triangle, and that has a height of 4, all right, and a base of 3, so if I go over 1, 2, 3, okay, if I want this to go a line that is going down from left to right, then this height needs to go down 4. So 1, 2, 3, 4. And there we go. So 3 and 4, there's my right triangle. This is a -4 if you want to throw that in there, but I'm talking about in the sense of triangles. So then we go ahead and connect and continue on. So next point, over 3, down 2, down 4, there we go. And then we go ahead and we can connect these all up. Sorry, this isn't going to be exactly perfect, but here we go. All right, so there's the line that shows that image. And now what I'm going to do is get rid of my right triangle, so I just have the line showing. So now what we have from here is we can go to the next one. And the next one, I'm just going to show this one. It's important if you want to rewrite it that you can put it into y equals mx plus b form. Just so you know, I will show this one both ways with the x-intercepts and y-intercepts, and also with y equals mx plus b. And really, it's a matter of determining which one you kind of like the best. So I'm going to get rid of this work here so I have somewhere to work. All right. So I have x minus 3y equals -18. So I can convert it into y equals mx plus b to start off with. So that's the first thing I'm going to go ahead and do. The things that are in my way are this x and this -3. Well, the x is associated with the 3, if I think about that first, and the y by an addition or a subtraction. So the easiest thing in the world is get the x out of there. If I want the x out of there, I just make it negative on the other side. Easy enough. If it were negative already, it would just be positive over here. So the idea of opposite side, opposite sign is a very unique, easy thing to do in an equation. So what I now have is -3. Don't be the other rookie mistake and drop that negative, right? Because it's a -3. I got rid of the x, not the minus, okay? So this is a -3y equals mx plus b, not b plus mx. So we're going to put the x first. So this is a -x. So I'm just keeping the signs with it. -x and then -18, and that's okay. Last step, I want y by itself. So what I'm going to do here is I'm going to make a fraction. I want the coefficient to be 1. Well, if I want a number to be 1, I just put it over top of itself. So I put -3 over -3, and I've got the number 1. So there we go. There's my y. That's nice. Well, if I make a fraction out of this term, I got to make a fraction out of the other terms as well, because it's division. So throw a -3 there, throw a -3 there. So now, here's the one mistake that a lot of people make, okay, is that there is an x there. Okay, how many x's? Well, I just said a x. From English class, is a singular word, so therefore that number in front of it is a 1, right? It's not a 0. Mathematically, if I'm going to have a 0, there's nothing there. So if it was a 0, I wouldn't even put the x there, right? Think about it, okay? If there is a x there, then there's 1. It's singular. A is a, right? So I now have -1 divided by -3, which is, again, we're leaving it in fraction form of 1/3. Okay, even if it were reduced to a whole number, you should still leave it in fraction form because, again, we are going to be using a rate of change, which means we're going to be drawing a triangle, which means we're going to need 2 values for a height and a base. So 1/3, there's my x, -18 over -3, b, make it a whole number. So +6, fantastic, yes? So there we go. So now I have this in the form of graphing. So I go up to +6, so from the origin, I say, hey, you're not starting at the origin anymore. You're starting at the number 6. Boom, there it is. 1/3 height base of a right triangle. So first things I like to always draw is the base. So I'm going to draw my base of 1, 2, 3, right? And then I'm going to draw a height of 1. Now, my slope is positive. So therefore, I need to make sure as I read it from left to right, I'm going upwards. So the easy thing to do is, okay, after I have my base, I'm going upwards. There it is, a height of 1. This is 3. So the ratio is 1 to 3. So I go ahead and I connect my lines. Okay? Sorry I missed that dot a little bit, but that's okay, because what I'm really concerned and interested in, again, is how do these two lines interact on this coordinate plane? And the only interaction that they have occurs right here, and that ends up being the thing that I talk about, and that interaction is called the solution. It is called the only thing I've found that the way that they interact. And I look at, okay, where is that interaction at? Where do they intersect at? And they intersect at -3, +5. So the answer to this particular problem is -3, +5, and then I'm done. It's graphing. When you graph, think about right triangles, drawing a base, drawing a height, label them, they are right triangles, and think about this starting value is moving you up and down. Now I said I would do this also in XY intercepts for the second one, because 18 is divisible by 3 and -18 is divisible by +1. So the other thing I could have done is done XY intercepts, but I'm not going to go through that simply because if you notice here when I put it into this form, look where the x-intercept would have been, and if you can look at this, the x-intercept would have occurred off of my graph.